talk the second and third laws of thermodynamics. Okay, so this is 16.3 in the book. What are our lesson objectives? We will state and explain the second and third laws of thermodynamics. We will calculate entropy changes for phase transitions under standard conditions, and we will calculate entropy changes for chemical reactions under standard conditions. When we first started talking about thermodynamics, we defined a system as what we're working with and everything else in the universe as surroundings. So if we take the law of conservation of energy, we then find the entropy change of the system plus the entropy change of the surroundings is equal to the entropy change of the universe. It comes directly from the law of conservation of energy because entropy is a type of energy, so it needs to balance. So the second law of thermodynamics states that all spontaneous changes cause an increase in the entropy of the universe. So delta S universe will be greater than 0. Entropy is positive when it increases. There are many implications to the second law. When we do work, we must have a hot side and a cold side. We can only do work if a process is spontaneous, and by definition, because doing work is a non-spontaneous thing. So going from hot to cold is spontaneous and therefore increases the entropy of the system and the surroundings. Increases the entropy overall of the universe. If you do not have a hot and cold side, you cannot do work because you're not increasing entropy overall for the universe. Additionally, we will go from areas of high concentration to low concentration, and it'll become completely mixed. That also increases the entropy of the universe. So we talked about that whole process a little bit in the spontaneous systems talk. It'll be spontaneous if it's going from hot to cold, if it's going from high concentration to low concentration, matter and energy mixing, right? And the reason for that is it increases the entropy of the universe. Now that we have the overall idea, definition, let's talk some math. So let's go ahead and look at how this was derived, this result, that spontaneous processes would be always increasing entropy. We know that it's spontaneous if it goes from hot to cold. So let's have a hot object that we call system and a cold object that is the surroundings. We will then apply the definition of entropy. So delta S of the system is equal to Q reversible over T of the system. And the heat that we're taking out of the system is going into the surroundings. So we're going to put a negative on that. So delta S surroundings is equal to negative Q reversible over T of surroundings. Okay. Now, we know that Q reversible is equal to the magnitude of Q reversible is equal to the magnitude of negative Q reversible. So we have a perfect transfer if it's a reversible thing. We know that T of system is greater than T surroundings because we said that the system was hot. So if we then apply that information to our delta S, the magnitude of the delta S system is less than the magnitude of delta S surroundings. Why? Because if you put a large number in a denominator, it is smaller than a smaller number in a denominator. Therefore, delta S of the universe is equal to delta S system plus delta S surroundings, which is greater than 0. So entropy will be greater than 0 if we have a spontaneous change occurring, which is what we're doing here. All right. Now, when the temperature of the system is approximately equal to the temperature of surroundings, and again, Q reversible will be equal to negative Q reversible, then we'll have the result that delta S system is approximately equal to delta S surroundings. So basically, if the temperatures are the same, the delta S will be the same. And if that's the case, we get the delta S of the universe being equal to 0. If those temperatures are about the same, we didn't actually transfer heat, in which case the system is at equilibrium. So again, this definition holds. And if we end up with a situation where we're moving stuff from a cold thing to a hot thing, as far as heat, then we know that we had to put in energy to make that happen. That's all of refrigeration. And as a result, our delta S universe would be less than 0. So let's talk temperature dependence, because we know that, for example, phase changes are spontaneous at some temperatures and not spontaneous at others. So first thing we're going to do is we're going to determine if the change is spontaneous when water goes from liquid to gas with a phase change entropy of 118.71 joules per Kelvin by removing 44.3 kilojoules from the surroundings. Okay, so is it spontaneous when we do this thing? So at 95 K, we know that we are changing the entropy by 118.71, and the entropy of that is for the system. The system is that water. We are removing 44.3 kilojoules from the surrounding, removing that energy from the surroundings. So we put that in for delta S surroundings, and we put it over 368 K because that's the temperature. And when we solve this, we find that we have a negative 1.7 joules change in entropy. That is not spontaneous. We have not increased the entropy of the universe. And that numerical value matches up with what we would have expected. Yay! Okay, now let's try it at 105. So we'll plug in the same values, 118.71 joules per Kelvin, and we will have negative 44,300. And we'll put it over 378. When we do that, we get 1.5 joules. And we know that a positive number is increasing the entropy of the universe, and that is spontaneous. So let's talk about the third law of thermodynamics. The third law of thermodynamics states that the entropy of a pure perfect crystal at 0 Kelvin is 0. Why? We had from previous section that S was equal to K times natural log of W. K was Boltzmann constant, and W was the number of ways that you could arrange the stuff, the matter, and the energy. So at 0 Kelvin, we know that we don't have any kinetic energy. And in addition to that, all of our molecules in a perfect crystal are in fixed positions and they're not going to move. So there's literally only one microstate for a perfect crystal at 0 K. Therefore, since the natural log of 1 is 0, S is equal to 0. Cool. Now, how do we apply this information? Well, we have this concept of standard entropy. We call it S naught. It is the entropy of 1 mole of substance at 1 bar of pressure. Okay. So standard conditions, 1 mole of a substance at 1 bar of pressure. Now, that may be at 25 degrees Celsius or another temperature, but for our purposes, it'll be 25 degrees Celsius. So in the book, it says that that's the standard temperature, and it's not. Any temperature can be standard temperature. The thing that is standard about this is that it's 1 mole of a substance at 1 bar. The book is just trying to be less confusing, but I'm going to be slightly more confusing now and less confusing when you get to PChem. 25 is our standard because we're working at room temperature, but you can find tables for this for standard entropy at like 37 because it's a biological system and that's what you're interested in. You can do all sorts of temperatures, is what I'm getting at. Okay, entropy is a state function. So therefore, the sum of the standard entropies of the products minus the sum of the standard entropy of the reactants will be equal to the change in the standard entropy, which hopefully you're looking at that and you're going, that is suspiciously like Hess's law. And you are correct. As long as it's a state function, it shouldn't matter what path you take, you will still get the same value for the change in entropy, just like you did for the change in enthalpy. Cool. Okay, so let's apply this information. At standard conditions, what is the entropy change of P4 solid going to P4 gas? Okay, so we would expect that an entropy change going from solid to gas is going to be negative, because negative would be spontaneous, but it will be temperature dependent, right? But the general thing should be negative. Okay, so let's try this thing. At standard conditions, we've got 1 mole at 1 bar. From our table, it's going to be 25 degrees Celsius. Our table is G1 in Appendix G at the very end of the book. So we always do our final state minus initial state for these types of problems. And we get a change of negative 115.6 joules per Kelvin, because when you go to a gas, you increase the amount of entropy, so this does actually make sense. Now let's try this for a chemical reaction. If ethanol is burned at 25 degrees Celsius, what is the change in entropy for the reactions? The first thing we need is a balanced chemical equation. Okay. So 1 mole of ethanol plus 3 moles of oxygen becomes 2 moles of carbon dioxide and 3 moles of water. Water in liquid state. Ethanol in liquid state, and oxygen and carbon dioxide as gases. Okay, so we're going to go ahead and look at Appendix G, table G1, and we'll find the delta S, or the S's. Okay, so I've color coordinated these, but I've also put them right under what they go with. My strong suggestion to you is when you are doing these problems, do the same thing. Put the numbers underneath the thing that they correspond to, and then do the math. Okay, and I literally, back in the day, used to check things off as I went to make sure that I got all the things, because otherwise I'd skip stuff accidentally and I'd be like, I am a dumbass. And I hated that feeling. So, ways to make sure you don't mess up. So we're going to do products minus reactants. We have to multiply by the number of moles because our standard enthalpy is for 1 mole of stuff, but we don't necessarily have just 1 mole in this chemical equation. Okay, so we have 205.2 times 2, which is for the CO2, plus 70 times 3, which is for the water, minus, in parentheses, because we want to do all this stuff as negative, 160.7 times 1, plus 3 times 213.8 joules per Kelvin. And you end up with negative 181.7 joules per Kelvin is the standard change in entropy for burning ethanol. So you're familiar with these problems. You've done similar things with entropy, or sorry, not entropy, with enthalpy. You're just going to apply it to entropy now. And I will warn you right now, you now have multiple things to watch out for when you're looking stuff up on tables. So make sure you're looking at the right line of the table, make sure you've got the right phase of the material, and make sure that you are reading off entropy, not enthalpy or Gibbs free energy, or Gibbs energy as we're probably going to call it. So just FYI, it's confusing and detail oriented, and just use a straight edge to read off the table because your life will be greatly improved. Your sanity will be greatly improved if you just use, like a piece of paper. Make sure you're reading the right line. It's so painful to have read the wrong line and come up with the wrong numbers. Just use a piece of paper as a guide. It'll work every time. Makes your life easier. Okay, so let's go on to the summary slide. So what are our takeaways from all of this? Delta S of the universe is equal to delta S of systems plus delta S of surroundings. The second law of thermodynamics states that all spontaneous changes cause an increase in the entropy of the universe. In other words, delta S of universe is greater than 0. The third law of thermodynamics states that the entropy of a pure perfect crystal at 0 Kelvin is 0. And due to that, we know that we've got a state function. So the standard entropy, S naught, is the entropy of 1 mole of a substance at 1 bar of pressure. And finally, because of that, the sum of the entropy of the products minus the sum of the entropy of the reactants is equal to the standard entropy change for a reaction.